and we're primarily going to be talking about the motivation for databases. So I'll give you a chance to answer this on Moodle. Why do we need databases? That's sort of the question. And the sub-question here, where's the data stored when Java's running? So if you're running a Java program and you've got some data structures, where are those stored? Go ahead and answer that, and then we'll come back. Did you say RAM? If so, then you're correct. So if you're running a Java program, whatever data structures you're creating, trees, maps, graphs, whatever, those are all actually stored in RAM. What's wrong with RAM? What are some of the disadvantages? I'll give you a chance to go ahead and plug that in for the second question there. So basically RAM is temporary. It's ephemeral, if you will. It's not saved after a crash or after the program ends. So whatever's in RAM, it just goes away. The machine reboots, RAM gets reset. So for a database, we actually don't want that. And actually, there's an acronym, ACID, ACID, which stands for Atomic Consistent Isolation and Durable, or isolated, I guess, and durable. And so these are all of the properties, all the features of a database that we would like to have. And these address some of the persistence issues that we just ran into with RAM because we don't want things to be ephemeral. So the idea here is that blocks of instructions, they either all happen or none of them happen. That's what we want by atomic. Atomic from the word atom, meaning, the smallest possible unit that can't be divided, which is of course ironic given that atoms are actually made up of subatomic particles like protons, neutrons, and electrons, which are themselves made up of even smaller particles. But regardless, the word atom means indivisible. So atomic, we want to have blocks of instructions that are essentially not divisible. And consistent, we want to move from one consistent state to another. We never want to stop at some inconsistent intermediate state. So those are two of the properties we want, and we'll kind of start with those. So, you can imagine some ATM software for some sort of banking system where you can withdraw money. So you imagine your standard, CS141 method. We're going to withdraw. You give it a double, that's the amount of money to withdraw, and there's a boolean that returns true if the withdrawal is successful and false if it fails. If the balance, we're assuming that this balance here, this is an instance variable, is greater than or equal to the amount, deduct the amount from the balance, then return true that it was successful. Essentially, this is an else, return false. So that's sort of your basic, very, very simple withdraw method for some sort of ATM or bank account system. So here's the question. Suppose there's simultaneous ATM withdrawals using that previous withdrawal method that we saw. Now here's the other assumptions. There's $500 in an account. It's shared between two people. Both of them have their own ATM card, so there's two ATM cards for the account. And they withdraw $500 at the same time at different locations. So at the same minute, the same second even, they're withdrawing from different ATMs at the same time. So what are the possible outcomes? And I'll give you a chance to plug this into Moodle and try to answer it and see what you come up with. So it turns out that A and B are both possible. It could be the case that one of them gets 500 and the other gets 0. And actually, since we're not specifying which is one and which is other, this actually covers sort of two cases. But it's actually possible that they both get $500, which they want, but the bank does not want. It's actually not possible that both are going to get $0. So B is obviously not surprising. A is actually surprising, because there's only $500 in the account. How can both of them get $500? Well, if we think about it, there's two withdrawals happening, which means that this withdrawal method is being called twice. Now, we're going to add over here this little arrow here. This is basically the timeline. And so you can imagine it's not the case that these things are literally happening at the same time. I mean, maybe they're literally doing their withdrawal at the same time at these different ATMs, but both of those ATMs have to talk to whatever bank actually is holding on to, or whatever system actually manages the physical money in the account. In other words, there's some instance of a bank account that these withdrawal methods are going to be invoked on. And so even if they're invoking it at the same time, it's not literally the case that for a single method you can be doing everything at exactly the same moment. So this is a possible interleaving. It may be that at time like t1 here, one of the ATMs is able to check that the balance is greater than or equal to the amount. Then at time t2, this one over here, this is able to figure out, well, is the balance greater than the amount? And it is, because greater than or equal to the amount, because the amount is 500, the balance is 500. So this may deduct the amount and return true. And then we jump back over here. This is going to deduct the amount and return true. There's some sort of total ordering that these statements are going to execute in. And so basically, as long as one of them checks the balance, then the other one checks the balance, before either of them do any deducting, then you're going to be in a situation where you end up withdrawing $500 from both accounts. And so this is not something that we want. And so one of the things databases give you through transactions is the ability to essentially say begin atomic block, have your code, and then say end atomic block. For those of you who have seen multi-threaded programming in Java, you know about synchronization. Basically what we're saying is we want this to be a synchronized block. If you haven't seen that yet and you're just learning about databases, that's fine too. Conceptually, we're saying these instructions, these are a block. They should be atomic. They should be indivisible. It should, in other words, it never should be the case, to go back a slide, that we should get this bad interleaving. We should never get this particular kind of an order. So by trying to make these atomic, what that should mean is, here's one possible ordering. All of the atomic section runs for one ATM machine, then for the other. Here's the other possible ordering, and no other interleaving should be possible. And so some of the terminology that you'll hear in databases, these are called transactions. You'll also hear the terms commit and rollback. So in database speak, database parlance, an atomic block is called a transaction. Ending a transaction, that's called a commit. So after you've done your transaction and you're happy with the changes that have been made, you can then commit those changes, and that will go ahead and change the underlying state. Now, if a transaction fails to commit, which is usually because another transaction kind of got there first, you'll get what's called a rollback, which will basically undo all of the changes of whatever transaction got there second. Now, the reason that we need commits and rollbacks, whereas in Java we just kind of have synchronized, synchronized is sort of blocking. So if you need to acquire a lock, in other words, you need to execute some sort of atomic block, but somebody else is already doing an atomic block, you have to just wait until they're ready. Databases actually allow you to kind of speculate a little bit and have sort of both people proceed as if everything's fine until one of them commits. And then once there's a commit, that actually is what changes the underlying state. So then when the second thread gets there and sees that a commit's been made, it's then going to get rolled back. Now, one of the other C, that was all under atomic. The other C in ACID is consistent. So crashes within an atomic section shouldn't put us into some inconsistent state. So this is sort of part of these rollbacks. So suppose this is a atomic section. We're going through a bunch of actors, and then we're adding the actors to the movie. Now suppose this loop crashes after half of the actors in this actor list have been added to the movie. Well, when we go ahead and try to restore after this crash, the movie's in an inconsistent state because only half the actors have been added to it. So if we sort of rerun this code, some actors will be in there twice, some will only be in there once. We would never want that to happen. And so what you would do, you would begin a transaction, you would sort of do this, and you would commit, and if this crashes, well then we can actually roll back the changes. So that's atomic and consistent. The ID of ACID, isolation, and durable. Isolation, changes should be isolated from one another until one of them's committed, and then durable means that committed changes can survive a program crash. Actually, should be able to survive even disk crash, potentially. So isolation, we need to support multiple transactions happening at the same time. Sort of canonical example of this, 18 people on Amazon, they might have the last copy of Bruce Campbell's autobiography all in their shopping cart. Since the shopping carts are virtual, this doesn't matter. They can all think they have it there. What's really going to matter, though, is whoever actually tries to buy it first. And it may not even be who tries to buy it first. It may be whoever gets their credit card charged first, or whoever actually completes the order first. So it may be that there's only one copy left. 18 people have it in their cart, but if nobody ever tries to buy it, then who cares that 18 people have it in their cart? It really matters once commits start getting made. So here's a question about these sort of conflicting transactions. So suppose we have two transactions and they've both added the last copy of this book to their shopping cart, and they're both trying to buy the book at the same time. And so the question is, who actually gets the book? So is it the first transaction that added the book to the shopping cart, the last one that added it to the shopping cart? Did neither of them get it for whatever reason, or do both of them get it, or do we not care? So I'll give you a chance to answer that on Moodle. So it turns out we actually don't care. This may not be fair. In other words, I may have added the book to my shopping cart a month ago, and you may have added it 5 minutes ago, and you may be the one that gets the book. But with ACID, we're not so much interested in fairness as we're interested in correctness. So for this particular situation, we actually don't care who gets the book as long as only one of them gets it. If both of them get the book, then we care. But if one of them gets the book, we actually don't care who gets it. So this is part of consistent. The database is in a consistent point, consistent state, as long as exactly one person gets the book. Now we may want fairness. We may want whoever gets it into their shopping cart first, they're going to have some sort of a priority. But that's a feature, not a requirement. And high-end commercial databases, like from Oracle, they may provide fairness. But you can also build fairness on top of just a basic database like MySQL, as some people call it. And that's fine. You can certainly build fairness into things because remember, fairness, that's a really good feature. Maybe it's great, but it's not really a requirement for correctness. So durable databases should be able to be restored from backups. We should never be at the mercy of like one disk crash, sort of losing everything. Excuse me. Yeah, you can tell I'm doing this at fairly late at night, and I got to teach FP at 8 o'clock tomorrow morning. So in Java, we actually have instances of a class that'll have several fields or instance variables. In a relational database, you actually have rows of a table that have several columns. So there's kind of a mapping between these ideas. And just a word about database types for a moment. So a database, this is the basic unit a table is the basic unit for collecting data in a database. A table is made up of multiple columns. So these are similar to, but they're not exactly the same as instance variables. And then tables actually support a lot of sizes and actually varieties of column types. So string, integer, double, date, blob, which stands for binary large object, basically some sort of binary data. Integers have a large variety of different sizes in MySQL, so a tiny int is 8 bits all the way up to a big int, which is 64 bits. And then here's a good link for that. So in Java, if we want to represent like an actor for a movie database, we might have a class called actor, we might have a string called name, and an int called age, and then another int for like the number of appearances in Us Weekly or US Weekly. Actually, I have no idea how that's pronounced. I just know it's like the one that all the actors like end up in. On the database side, we would have a table, these are the column types and sizes. So name, it's a varchar, that's basically a type of string, a variable length string or variable length character string. They can be up to size 100. We have age, might be a small int, because small int, as you'll recall, is up to 16 bits. 8 bits, that's up to unsigned would be 200, 0 to 255. Signed would be negative 127 to 128, or negative 128 to 127. Yeah, that sounds right. So, we may want to make this a small int just in case there's like some actor that lives to be like 200 or 300 years old or something like that. And then, number of appearances, this is obviously another type of int. And so the next lecture, what we're going to talk about is how to actually start thinking about this structure, relating these tables to each other, and actually sort of building and manipulating this using a database administration tool called PHP MyAdmin.